After studying this module, you shall be able to know the importance of Tanabe Sugano diagrams as well as learn the interpretation of these diagrams. You will identify the parameters involved in the calculation of energy for the various transitions, and you can analyze the various types of transitions feasible in the complexes. Introduction. So first of all, we should know that what is a Tanabe Sugano diagram. Tanabe Sugano diagrams are a special class of correlation diagrams in which the lowest energy free ion term is plotted as x-axis and all the other terms are plotted relative to this lowest energy term. They plot energy of different groups of degenerate electronic states as a function of Ligand field strength. The parameter capital B is the Raka parameter, which is the repulsion term which arises due to repulsion between the terms of same spin multiplicity. The ordinate is represented as capital E by capital B, and the abscissa is given as the value of delta upon the value of B. These diagrams can be qualitative as well as quantitative in nature, but mostly the results drawn are qualitative in nature. In cases where both high spin as well as low spin complexation is possible, that is in the cases of D4, D5, D6 and D7 electronic configurations, a vertical line is drawn in the middle of the diagram in order to separate the high spin complexes from the low spin ones. The general Tanabe Sugano diagram has been represented in figure.
Let us understand the Tanabe Sugano diagrams by discussing its important features. These are the special type of correlation diagrams which have some important features which have to be analyzed in order to completely interpret them and understand their importance in understanding the electronic spectra of the coordination complexes. The features can be given as: in these diagrams, the lowest energy term, which is the ground free energy term, is plotted on the horizontal axis, that is the abscissa or the x-axis. The excited states are also represented above ground state term according to their increasing energy levels. The energy above horizontal x-axis directly represents the energy of excited states above the ground free energy term, or we can say it shows the amount of energy by which excited states are destabilized in comparison to that of the ground state. The free energy terms in absence of Ligand field are represented on the left and the strong field Ligand terms on the extreme right. The two extremes are joined with the help of lines depicting the change as we go from no field towards the high field conditions. In between, we can have the weak field cases. Generally, weak and strong field cases are separated in between the diagram by a vertical line which divides the two possible orientations. At the dividing line, ground state also changes. Various parameters represented on the x and y axis are stated as follows. On the x-axis, delta naught by B, where delta naught is the octahedral Ligand field splitting parameter, is represented, which increases in the value as we move from left to right in the diagram. On the y-axis, E by B, where E is the energy of the excited states above the ground state term is represented. Its value increases on moving up from down along the vertical distance. Capital B represents the Raka parameter, which is the repulsion parameter that measures the extent of repulsion between the terms of same spin multiplicity. The lines joining the free ion terms and ligand field terms follow non-crossing rule, according to which terms of same spin multiplicity do not cross each other. Next is the interpretation of the spectra. The Tanabe Sugano diagrams are very useful in interpreting the electronic spectrum of the coordination compounds. For various electronic configurations, Tanabe Sugano diagrams are drawn, which will be discussed under the following heading along with important features of each configuration. Firstly, let us discuss the D1 configuration. For the D1 electronic configuration, number of electrons is 1, and thus the Tanabe Sugano diagram is also quite simple to be drawn and to interpret. The configuration can be represented as T2G1 Eg0. Now, the excitation of the electron from the lower T2G level to the upper Eg level forms the excited state. The spin multiplicity of the ground and excited state is same, and hence the transition from the ground to the excited state is spin allowed transition. The examples of the D1 configurations include titanium 3 plus complex, chromium 2 plus complex, and the copper 2 plus complex, etc. The Tanabe Sugano diagram along with the absorption spectrum can be represented as follows in figure. From the figure, it can be seen that only one transition is possible from the ground doublet T2G to the excited doublet EG state. Thus, only one transition band should be observed corresponding to the value of delta naught. But in the actual practice, a single absorption band is splitted up into two, as can be seen from the absorption spectrum. This actually occurs due to the Jane-Taylor distortion, which leads to the splitting of the single band into two. Also, it can be seen that no Raka parameter is involved in the diagram, since only single excited state is possible. Next, we are going to discuss the D2 configuration. For a D2 configuration, the Tanabe Sugano diagram is a bit complicated in comparison to that of D1 configuration. In this case, the free ion term of ground state is triplet F, which splits up into three states of same spin multiplicity, namely triplet T1G, triplet T2G, and triplet A2G. The next higher term of same spin multiplicity is triplet P, which transforms as triplet A2G in the presence of the ligand field. Since the configuration in the weak as well as strong field is same, the diagram is only in terms of ligand field irrespective of the applied field, weak or strong. The Tanabe Sugano diagram for the D2 configuration along with absorption spectrum is shown in figure. An example of a D2 configuration is given by the complex of vanadium H2O 3 Its electronic spectrum is shown in figure. Under ordinary condition, the most populated state is the ground state triplet T2GF. The excitation leads to three spin-allowed absorption bands, namely mu1, mu2, and mu3, given in the diagram. These leads to three transitions as follows. Mu1 corresponds to triplet T1GF to triplet T2G. Mu2 corresponds to triplet T1GF to triplet T1GP. Mu3 corresponds to triplet T1GF to triplet A2G. Here is shown the Tanabe Sugano diagram and the absorption spectrum for the D2 configuration along with the absorption spectrum. From the absorption spectrum, it can be seen that only two transitions are observed corresponding to mu1 and mu2 at 17,800 and 25,700 centimeter inverse. The third band, mu3, lies at 38,000 centimeter inverse, which is out of the scale for the spectrum and is mostly overwhelmed by the charge transition bands in that area. Now, in order to determine the value of delta naught from the spectrum given, we have to take in consideration the fact that the terms of the same symmetry and multiplicity tend to mix with each other, and thus we can say that there occurs a mixing of triplet T1GF and triplet T1GP. Because of this, the lines connecting these two states with free ion terms tend to be slightly curved than expected. Hence, the value of delta naught cannot be simply determined by just determining the value of mu1. The alternate method is to find difference between the states with T2G1 Eg1 and T2G0 Eg2 electronic configurations. Thus, the value of delta naught will be the difference of the energy between triplet A2G and triplet T2G. The intricacy with this concept is that lines of triplet T1GP and triplet A2G cross each other. Moreover, because of this, the band positions alter in the weak and strong field cases. Hence, it becomes very difficult to understand the exact position of the transitions and thus the value of splitting parameter. In this kind of complicated situation, it is better to first determine the value of Raka parameter and thus using that conclude the value of ligand field splitting parameter delta naught. Here we will take a D2 case of vanadium 3 plus complex for which the value of mu1 and mu2 is 17,800 and 25,700 centimeter inverse. For these compounds, this corresponds to the transitions from triplet T1GF to triplet T2GF and from triplet T1GF to triplet T1GP. Now we will determine the value of mu2 upon mu1, which in this case comes out to be mu2 upon mu1 is equal to 1.44. From the Tanabe Sugano diagram, it can be seen that the ratio of mu3 upon mu1 comes out to be approximately equal to 2. Hence, the value of 1.44 definitely corresponds to the ratio of mu2 by mu1. The ratio varies as the function of the value of delta naught. Hence, a plot can be drawn between delta naught by B and mu2 by mu1. The plot is shown in figure. From the figure, it can be seen that when the value of mu2 by mu1 is 1.44, the value of delta naught by B is 31. Now, by looking at the Tanabe Sugano diagram, it can be observed that when delta naught by B is 31, the value of E by B mu1 is approximately equal to 29. Thus, if E by B is equal to 29, where the value of E is 17,800 centimeter inverse, the value of B automatically comes out to be 610 centimeter inverse. Therefore, delta naught will be equal to B into the value 31, which is equal to 19,000 centimeter inverse. Hence, the value of delta naught for the complex comes out to be 19,000 centimeter inverse. Next, we will come to the D3 configuration. For a D3 configuration, the electronic arrangement in the weak as well as the strong field is T2G3 Eg0 as the ground electronic state. In the excited state, an electron from the lower T2G level is shifted to the Eg level. Thus, the configuration changes to T2G2 Eg1. The ground state has F as the lowest energy term, which in the presence of the ligand field splits into A2G, T2G and T1G. The difference between the two lowest energy terms corresponds to the value of delta naught. Therefore, in order to find the value of delta naught, we simply have to determine energy difference between the A2G and T2G states. The Tanabe Sugano diagram for this configuration can be represented in figure. Examples of this electronic configuration include the chromium 3 plus complex having the aqua ligand in the octahedral geometry. Figure 6 shows the Tanabe Sugano diagram and the absorption spectrum for the D3 configuration.
Summary. Tanabe Sugano diagrams are a special class of correlation diagrams in which lowest energy term is plotted as x-axis and all the other terms are hence plotted relative to this lowest energy term. These diagrams plot energy of different groups of degenerate electronic states as a function of ligand field strength. The free energy terms in the absence of ligand field are represented on the left, while strong field terms are represented on the extreme right. Delta naught by B is represented on the x-axis, where delta naught is the ligand field splitting parameter, which increases in the value as we move from left to right in the diagram. E by B is represented on the y-axis, where E is the energy of excited states, the ground state term. Its value increases on moving up from down along the vertical distance. Capital B represents the Raka parameter, which is the repulsion parameter that measures the extent of repulsion between the terms of same spin multiplicity. The lines joining the free ion and the ligand field terms follow the non-crossing rule, according to which the terms with same symmetry cannot cross each other. In the case of D1 configuration, only one transition is possible from the ground doublet T2G state to the excited doublet EG state. Thus, only one transition band should be observed corresponding to the value of delta naught. But actually, two bands can be seen because of the Jahn-Taylor distortion, which leads to the splitting of a single band into two. For the D2 configuration, the Tanabe Sugano diagram is a bit complicated in comparison to that of D1 configuration. In D2 case, the free ion term of ground state is triplet F, which split up into three states of same spin multiplicity, namely triplet T1G, triplet T2G and triplet A2G. The next higher term of same spin multiplicity is triplet P, which transforms as triplet A2G in the presence of the ligand field. Under ordinary conditions, the most populated state is the ground triplet T2G capital F. The excitation leads to three spin allowed absorption bands, namely mu1, mu2 and mu3, as given in the above diagram. These transitions are: mu1 gives triplet T1GF to triplet T2G. Mu2 is by triplet T1GF to triplet T1GP. mu3 is by triplet T1GF to triplet A2G. There occurs a mixing of triplet T1GF and triplet T1GP states. Because of this, the lines tend to be slightly curved than expected. Hence, the value of delta naught cannot be simply determined by just determining the value of mu1.